Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the quiet realm of Earth's cosmic guardians, the patient sentries that watch our skies for wandering stones from the deep. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. In the high desert of Arizona, where ancient meteor craters still dimple the earth like forgotten coins pressed into clay, a new kind of watching begins. The Catalina Sky Survey Telescope moves with mechanical precision across star fields that have remained unchanged for human lifetimes. Its electronic eye drinking in photons that have traveled for millennia, only to reveal the presence of something much closer to home. Night after night, this robotic sentinel scans the same patches of sky with the patience of geological time itself, looking for the one thing that shouldn't be there, the moving dot that betrays a visitor from the asteroid belt, a wanderer that has broken from its ancient orbital dance. The telescope doesn't know it's making history. It simply follows its programming with the quiet dedication of tidal forces, taking image after image, each one a snapshot of cosmic real estate where nothing should change across human timescales. But change is exactly what it seeks, the subtle motion that speaks of gravitational conversations between worlds. A rock the size of a city block, drifting in the space between Mars and Jupiter for millions of years, occasionally finds itself nudged by forces larger than planets. Perhaps Jupiter's immense pull gives it a gentle push, or maybe the solar wind catches it at just the right angle during a particularly active solar cycle. The asteroid doesn't resist these cosmic suggestions. It has no choice but to comply, beginning a new trajectory that will carry it through space for eons, one that might, in the distant future, intersect with Earth's own orbital path around the Sun. The irony settles, like interplanetary dust, humanity's most sophisticated early warning system depends entirely on detecting the absence of stillness in a universe built fundamentally on movement. Every star visible in Earth's night sky follows predictable paths through the galaxy. Every planet maintains its elliptical dance around the Sun. Every grain of cosmic debris obeys the same gravitational laws that have governed celestial mechanics since the solar system's birth. Yet this very predictability makes the exceptions visible. Like a single leaf falling upstream in a river, when an asteroid breaks from its expected course, deviating even slightly from astronomical predictions, it becomes, for a brief moment in geological time, humanity's immediate concern. The mountains surrounding the Catalina Observatory have witnessed 4.5 billion years of cosmic bombardment. Embedded in their ancient rocks lie the remains of meteorites that fell when Earth was young, when the atmosphere was thin and the surface molten. These stone witnesses remember when asteroid impacts were common, when the early solar system was still clearing its debris, when collisions shaped continents and boiled oceans. Now, in an era of relative cosmic calm, the same mountains shelter instruments designed to prevent what once was inevitable. What the telescope cannot see, but what scientists have calculated with growing certainty, is that space contains far more wanderers than anyone imagined just decades ago. The region between Mars and Jupiter, once thought to contain perhaps thousands of significant asteroids, actually hosts millions of rocky fragments ranging from pebbles to mountains. Most drift harmlessly in stable orbits, too small to threaten Earth or too distant to ever cross its path. But some, perhaps tens of thousands, follow trajectories that bring them uncomfortably close to Earth's neighborhood. Close enough that their future positions require constant monitoring and recalculation. The asteroid belt itself tells a story of planetary formation interrupted. Where a world might have coalesced from the primordial disk of gas and dust that surrounded the young sun, Jupiter's gravitational influence prevented the scattered material from gathering into a single body. Instead, countless fragments continue their eternal dance, occasionally perturbed into new orbits that carry them toward the inner solar system. Some become meteor showers, burning up harmlessly in Earth's atmosphere as streaks of light. Others, the larger ones, the city killers and continent shapers, require a different kind of attention. The mystery lies not in their number, but in the timing of their discovery. Why now, after 4.5 billion years of Earth's existence, does humanity finally look up with systematic purpose? The planet has survived countless impacts, from the collision that likely formed the moon to the event that ended the age of dinosaurs. Life has persisted through bombardments that would sterilize worlds, evolved during periods when the skies regularly fell, adapted to a cosmos that seemed actively hostile to complex organisms. Yet only in the past few decades has Earth's dominant species developed both the technology to detect approaching threats and the theoretical capability to deflect them. Perhaps it is simply coincidence. The same industrial revolution that gave humans the power to alter their planet's climate also provided the tools to survey its cosmic neighborhood. Or perhaps there is something deeper at work, an evolutionary pressure that drives intelligence toward planetary defense once it reaches a certain threshold of capability. The universe offers no answers to such questions, only the steady accumulation of data from robotic eyes that never blink, never tire, never lose focus in their patient cataloging of cosmic neighbors. In the control rooms where this data flows like digital rivers, technicians monitor screens that display the positions of thousands of tracked objects. Each point of light represents a world in miniature, a fragment of ancient planetesimal that has wandered the solar system since before Earth had continents, before the sun settled into its current stable luminosity. Some of these wanderers have names now: Apophis, Bennu, Didymos, appellations that transform anonymous rocks into characters in humanity's expanding cosmic narrative. The naming itself reveals something profound about the human response to existential threat, the impulse to domesticate the unknown through language, to transform vast impersonal forces into manageable categories. An unnamed asteroid is pure potential energy, a mathematical abstraction defined by orbital parameters and impact probabilities. But Apophis, named for an ancient Egyptian deity of chaos, becomes something else entirely, a known quantity that can be tracked, studied, and perhaps eventually deflected. The telescope continues its sweep across the star fields, immune to such philosophical considerations. Its purpose is simpler: to see what moves against the background of cosmic stillness, to identify the exceptions that prove the rule. In the vast spaces between worlds, where radiation pressure and gravitational perturbations play out over millions of years, time moves differently than it does on Earth's surface. What appears to human observers as sudden celestial motion actually represents the culmination of processes that began when continents were young, when species existed that left no fossils, when Earth's rotation was faster and its days were shorter. On a February morning in 2013, the city of Chelyabinsk awakens to an ordinary Russian winter, its residents bundling against the cold as they have for countless generations. The sky holds no warnings, no celestial omens to suggest that this day will be different from any other. Factory workers begin their shifts, students hurry to classes, and commuters navigate icy sidewalks with the practiced ease of those accustomed to harsh seasons. Above them, traveling at nearly 40,000 miles per hour. A visitor from the asteroid belt completes its million-year journey toward an appointment with Earth's atmosphere. The meteor measures perhaps 60 feet across, small by cosmic standards, barely large enough to register on the scales that astronomers use to categorize potentially hazardous objects. For comparison, the asteroid that likely ended the Cretaceous period measured 6 miles in diameter, a mountain-sized projectile that released energy equivalent to billions of nuclear weapons. This Chelyabinsk visitor carries far less destructive potential, yet still represents more kinetic energy than humanity has ever deliberately released in a single instant. It approaches from the direction of the sun, invisible to ground-based telescopes, undetected by the survey programs that scan the night sky for such wanderers. The entry begins at an altitude where commercial aircraft cannot fly, in the thin atmospheric layers where Earth gradually yields to space. Here, molecules of nitrogen and oxygen exist in sparse concentrations, barely dense enough to interact with the incoming stone, but interaction is inevitable. And as the meteor plunges deeper into Earth's protective envelope, friction begins its ancient work. The rock's surface heats beyond the melting point of iron, then beyond the temperatures found in blast furnaces, then beyond anything achievable in earthly laboratories without specialized equipment. What happens next unfolds in seconds but reverberates across decades of planetary defense planning. The meteor's leading edge, compressed by atmospheric resistance, reaches temperatures of several thousand degrees Celsius. The rock itself, composed of materials that formed in the cooling nebula around the young sun 4.5 billion years ago, begins to ablate, a gentle scientific term for the violent process by which solid matter transforms directly into plasma. Fragments break away like sparks from a cosmic anvil, each one tracing its own brief arc across the Siberian sky. The light comes first, as light always does. A brilliant flash illuminates the winter landscape with the intensity of multiple suns, casting sharp shadows that swing wildly as the fireball blazes across 60 miles of sky in mere moments. Dashboard cameras, ubiquitous in Russian vehicles due to insurance regulations, capture the event from dozens of angles, an accidental scientific windfall that provides researchers with unprecedented documentation of a major meteor event. The footage reveals details invisible to human perception, the way the fireball pulses and fragments, the specific colors that indicate the meteor's composition, the precise trajectory that allows scientists to calculate its origin in the asteroid belt. But the most significant moment occurs not during the meteor's visible flight, but afterward, when the sound waves arrive. The explosion, occurring at an altitude of about 15 miles above the Earth, generates an acoustic shock that propagates downward through increasingly dense atmospheric layers. When these pressure waves finally reach the surface, they arrive with the force of distant thunder, but thunder amplified beyond anything produced by terrestrial storms. Windows throughout Chelyabinsk shatter almost simultaneously, more than 20,000 panes of glass, transforming into cascades of crystal fragments that catch the winter sunlight like scattered diamonds. The irony of the Chelyabinsk event settles over the scientific community like morning frost on the very same day that astronomers worldwide focus their attention on asteroid 2012 DA14, a well-tracked object making a record-close approach to Earth. An entirely different and undetected visitor delivered a reminder that the cosmos does not always announce its intentions. The two events, unrelated except by cosmic coincidence, illustrated both the progress and the limitations of humanity's attempts to monitor its celestial neighborhood. One asteroid followed a predicted path with mathematical precision, passing harmlessly through the space between Earth and its artificial satellites. The other arrived without warning from the sun's direction, demonstrating that even the most comprehensive survey programs have blind spots. The Chelyabinsk meteor's composition tells its own story of deep time and cosmic wandering. Spectroscopic analysis of recovered fragments reveals a mixture of silicate minerals and metallic inclusions typical of ordinary chondrites, meteorites that formed in the early solar system from the same primordial materials that eventually coalesced into planets. These rocks carry within their crystalline structure a record of processes that occurred before Earth had a solid surface, before the Sun settled into its current stable phase of hydrogen fusion. In a very real sense, the Chelyabinsk meteor was older than continents, older than oceans, older than the distinction between day and night on Earth's surface. The mystery that emerged from the Chelyabinsk event concerns not what happened, but what didn't happen. Despite releasing energy equivalent to approximately 30 Hiroshima bombs, the meteor caused remarkably few serious injuries. Most of the harm came not from the explosion itself, but from flying glass and debris as shockwaves shattered windows across the region. This outcome reflects both the meteor's relatively small size and its fortuitous airburst at high altitude, which distributed its energy over a wide area rather than concentrating it at ground level. Had the same object arrived at a steeper angle or possessed a more robust internal structure, it might have reached the surface intact, creating a crater and far more devastating consequences. In the aftermath, as cleanup crews swept glass from Chelyabinsk's streets and scientists analyzed the event's implications for planetary defense, a subtle shift occurred in humanity's relationship with the cosmos above. The meteors served as an unexpected teacher, demonstrating that Earth's atmosphere provides more protection than previously understood. Even relatively large objects can be disrupted and their energy safely dispersed before reaching inhabited areas. Yet, it also revealed the limitations of current detection systems, the blind spots that allow mountain-sized rocks to approach unobserved simply because they travel from the wrong direction relative to ground-based telescopes. The children of Chelyabinsk, many of whom witnessed the fireball on their way to school that February morning, will carry the memory of that brilliant flash throughout their lives. They belong to the first generation in human history to grow up with the knowledge that their planet is actively monitored for cosmic threats, that telescopes scan the sky each night specifically to prevent surprise visits from the asteroid belt. Yet they also learned, in the most direct way possible, that such vigilance has limits, that the universe still holds the capacity for surprise despite humanity's growing technological sophistication. In the Catalina Mountains north of Tucson, where saguaro cacti stand like ancient sentinels against star-filled skies, a single telescope accomplishes what all of human civilization failed to achieve across millennia of skywatching. The Catalina Sky Survey, operating with the quiet persistence of desert seasons, has discovered more near-Earth asteroids than every observatory, every astronomer, and every civilization that preceded it. Night after night, year after year, its electronic eye sweeps across the same celestial territories, capturing images that reveal the slow choreography of rocks that have wandered the solar system since before Earth solidified from cosmic debris. The mountain that hosts this patient sentinel carries in its stone the memory of ancient impacts. Embedded in its granite foundations lie microscopic fragments of meteorites that fell when Arizona was an ocean floor, when the continents occupied different positions on Earth's surface, when the climate itself bore no resemblance to the desert that now surrounds the observatory. These geological witnesses remember bombardments that shaped Earth's early atmosphere, collisions that delivered water and organic compounds from the outer solar system, impacts that may have both hindered and facilitated the emergence of life itself. The telescope's methodology appears almost absurdly simple for an instrument that has revolutionized planetary defense. It takes multiple photographs of the same patch of sky, separated by intervals of 15 to 30 minutes enough time for a nearby asteroid to betray its presence through motion against the background of distant stars. The stars themselves serve as reference points, their positions so precisely known that any object moving relative to their fixed patterns becomes immediately apparent to computer algorithms designed to detect such anomalies. What appears to human eyes as random points of light reveals itself to digital analysis as a carefully ordered system in which every deviation from expected behavior carries significance. The desert air above the Catalina Mountains provides conditions that would have seemed miraculous to earlier generations of astronomers. At an altitude of over 9,000 feet, the observatory sits above much of Earth's atmospheric turbulence, allowing its instruments to achieve clarity that ground-level telescopes can only approximate. The lack of humidity eliminates much of the water vapor that absorbs infrared radiation, while the region's sparse population means minimal light pollution to interfere with observations of faint objects. These advantages, combined with Arizona's famously clear skies, create an environment where asteroids as small as houses become detectable across millions of miles of space. Yet the telescope's greatest achievement lies not in its individual discoveries, but in the systematic nature of its survey. Previous generations of asteroid hunters relied on chance observations, serendipitous discoveries made while studying other celestial phenomena. The Catalina Sky Survey operates according to a different philosophy: comprehensive coverage that leaves no patch of accessible sky unexamined for more than a few nights. This methodical approach has revealed that Earth's cosmic neighborhood contains far more potentially hazardous objects than anyone suspected when the survey began its operations in the late 1990s. The catalog that emerges from these nightly observations reads like a census of wandering worlds. Asteroid 1998, QE2, a contact binary nearly 3 miles long that rotates once every 4 hours while tumbling end over end through space. Asteroid 2005. YU-55, a dark carbonaceous object that passed closer to Earth than the Moon's orbit, offering scientists an unprecedented opportunity to study a potentially hazardous asteroid through radar observations. Asteroid 162173 Ryugu, whose diamond-shaped profile and rapid rotation suggest a rubble pile structure held together by gravitational forces so weak that a gentle push could scatter its components across the solar system. Each discovery carries with it a story that spans geological ages. These asteroids formed from the same primordial materials that created Earth, Venus, Mars, and Mercury, but followed different evolutionary paths determined by their positions in the early solar system. While the inner planets accumulated enough mass to become geologically active worlds with atmospheres and magnetic fields, the asteroids remained essentially unchanged since the solar system's youth. They preserve within their mineral compositions and crystalline structures direct evidence of processes that occurred before Earth had continents, before the Sun achieved its current stable luminosity, before the distinction between inner and outer solar system became clearly defined. The mystery that deepens with each new discovery concerns the unexpected diversity among objects that formed in similar regions of space. Some asteroids appear to be solid metallic cores, possibly the remains of larger bodies that were shattered by ancient collisions. Others consist of loose aggregations of smaller fragments, held together by gravitational forces so weak that they would collapse under their own weight if they possessed Earth-like surface gravity. Still others show evidence of having been heated and partially melted at some point in their histories, suggesting that even in the cold depths of space, internal radioactive decay or external energy sources can drive geological processes. The telescope cannot directly observe these internal structures, but orbital mechanics provides indirect evidence of asteroid composition and density. When an asteroid passes close to a planet or large moon, Gravitational interactions slightly alter its trajectory in ways that reveal its mass distribution. A solid metallic object responds differently to gravitational perturbations than a loosely consolidated rubble pile, allowing astronomers to infer internal structure from careful analysis of orbital changes. These subtle gravitational signatures, accumulated over years of observations, gradually build detailed portraits of objects that remain invisible except as moving points of light. The irony that emerges from decades of systematic observation is both humbling and encouraging. The more humanity learns about near-Earth asteroids, the more apparent it becomes that Earth has been extraordinarily fortunate throughout its geological history. Statistical analysis suggests that impacts capable of causing mass extinctions occur roughly once every 100 million years, yet Earth's biosphere has survived and thrived for nearly 4 billion years. This resilience implies either remarkable luck or previously unrecognized protective mechanisms that deflect or disrupt potentially catastrophic impacts before they reach the planet's surface. Perhaps Jupiter's massive gravitational influence serves as a cosmic shield, capturing or ejecting many asteroids before they can threaten the inner solar system. Perhaps Earth's large moon plays a role, its gravitational field helping to disrupt incoming objects or deflect them into less dangerous trajectories. Or perhaps the asteroid belt itself provides protection by preventing larger objects from forming through gravitational accretion, keeping potential planet killers fragmented into smaller, more manageable pieces that Earth's atmosphere can handle through airburst events like Chelyabinsk. The telescope continues its patient survey, immune to such theoretical considerations. Its purpose remains observational rather than explanatory to map the positions and trajectories of objects that share Earth's orbital neighborhood, to identify which ones might pose future threats, and to provide the data necessary for more detailed studies by other instruments. In the vast catalog of discoveries that grows each night, patterns emerge that speak to fundamental questions about planetary formation, orbital dynamics, and the long-term evolution of solar systems around other stars. On September 26, 2022, at exactly 23:14 UTC, a spacecraft no larger than a refrigerator completes humanity's first deliberate act of planetary defense. The Double Asteroid Redirection Test, known simply as DART, travels 7 million miles from Earth to intercept an asteroid moon called Dimorphos with the precision of a cosmic billiard shot. The collision occurs at 14,000 miles per hour, a speed that transforms the modest spacecraft into a kinetic projectile carrying the energy of several tons of TNT, yet representing barely a whisper compared to the forces that regularly reshape the solar system through gravitational interactions and solar radiation pressure. The mission's elegance lies in its simplicity. No nuclear weapons, no exotic propulsion systems, no science fiction technologies, just the fundamental physics of momentum transfer applied on an interplanetary scale. Isaac Newton's laws of motion, formulated 3 centuries earlier to describe falling apples and orbital mechanics, prove equally applicable to the challenge of nudging an asteroid onto a slightly different trajectory. The spacecraft carries no complex scientific instruments, no sample collection devices, no communication arrays designed for extended operations. Its purpose is singular and terminal to impact Dimorphos at precisely the right moment and angle to demonstrate that human technology can alter the course of celestial bodies. DART's journey to its target unfolds across 10 months of cruise through the inner solar system, during which the spacecraft follows a trajectory calculated years in advance by orbital mechanics specialists working with the same mathematical principles that govern planetary motion. The flight path appears almost leisurely by spacecraft standards, a gentle arc that intercepts Dimorphos not where it is at launch, but where it will be nearly a year later. This prediction of future positions across millions of miles of space represents one of humanity's oldest scientific achievements, refined over centuries of astronomical observation into computational methods so precise that they can deliver a small spacecraft to a target asteroid with accuracy measured in meters. The asteroid system that awaits DART's arrival exists in a gravitational dance that has continued unchanged for millions of years. Dimorphos. The primary body measures roughly half a mile in diameter and rotates once every 2 hours and 22 minutes, fast enough that loose material on its surface would fly off into space if not held in place by the asteroid's modest gravity. Around this spinning parent orbits Dimorphos, a smaller moon approximately 500 feet across that completes one revolution every 11 hours and 55 minutes. The two bodies remain locked in their orbital embrace by gravitational forces so weak that a strong human could theoretically escape their combined influence with a well-timed jump. Yet these same weak forces that barely hold the asteroid system together also ensure that any change in momentum will propagate through the system in predictable ways. When DART strikes Dimorphos, the impact energy will not simply dissipate as heat and fragmentation, it will alter the moon's orbital velocity around Dimorphos, changing the period of its revolution by a measurable amount. Ground-based telescopes can detect this change by monitoring the system's brightness variations, which occur when one asteroid passes in front of the other as viewed from Earth. These eclipses, or transits, happen with clockwork regularity, making any alteration in timing immediately apparent to observers millions of miles away. The spacecraft's final approach unfolds with the inevitability of celestial mechanics. DART's navigation camera begins capturing images of the Dimorphos system when the asteroids appear as nothing more than a point of light barely distinguishable from background stars. Gradually, over the course of several hours, the target resolves into two distinct objects, then into bodies with visible surface features, then into worlds with their own topography of boulders, craters, and ridges shaped by billions of years of micrometeorite bombardment and thermal cycling. The images that stream back to Earth during DART's final hour reveal Dimorphos to be what scientists term a rubble pile, not a solid piece of rock, but rather a loose collection of fragments held together by gravity so weak that the entire body would come apart if spun much faster than its current rotation rate. This structure, common among smaller asteroids, represents the remnants of ancient collisions that shattered larger parent bodies into pieces that gradually reaccumulated under their own gravitational attraction. The surface appears covered in fine regolith created by eons of bombardment by particles smaller than grains of sand, each impact contributing to the slow erosion and redistribution of material across the asteroid's surface. The mission's controllers on Earth can only watch as events unfold according to the immutable laws of physics. Radio signals take 14 seconds to travel between Earth and the Dimorphos system at the time of impact, making real-time control impossible. DART must execute its final approach autonomously, using onboard computers to identify its target and adjust its trajectory during the last 4 hours of flight. The spacecraft's artificial intelligence, programmed years earlier, recognizes Dimorphos from the images captured by its navigation camera and locks onto the asteroid moon with single-minded determination. The collision itself lasts perhaps a tenth of a second, the time required for DART's aluminum structure to crumple against Dimorphos's rocky surface and transfer its momentum to the larger body. High-speed cameras aboard a companion CubeSat, deployed from DART weeks earlier, capture the impact and its immediate aftermath, a brilliant flash, followed by an expanding plume of debris that continues to grow long after the spacecraft itself has ceased to exist as a coherent object. This debris cloud, composed of fragments excavated from Dimorphos's surface by the impact, creates a temporary comet-like tail that stretches for thousands of miles behind the asteroid as it continues its orbit around the Sun. The irony of humanity's first planetary defense test is that it occurs not in response to any immediate threat, but as a demonstration of capability for future contingencies. Dimorphos poses no danger to Earth. Its orbit around Didymos ensures that the smaller moon will never approach our planet closer than several million miles. Yet the mission's success proves that the technological infrastructure exists to mount a deflection campaign against a truly hazardous asteroid. Should one be discovered with sufficient advance warning, the key limitation lies not in engineering capability, but in detection timeframes. Most deflection strategies require years or decades of advance notice to be effective. The debris cloud that expands from the impact site carries with it material that last saw sunlight when the solar system was young, when Earth was still accreting from planetary embryos, when the distinction between asteroids and comets had not yet been clearly established. Spectroscopic analysis of this excavated material reveals the composition of Dimorphos's interior layers, providing insights into the asteroid's formation history and internal structure. The same impact that demonstrates humanity's capacity for planetary defense also serves as an unintended archaeological excavation of materials that preserve the chemical signatures of the early solar system. In the spaces between worlds, where solar radiation pressure competes with gravitational attraction and where a year passes unnoticed by any terrestrial standard, Dimorphos continues its ancient dance around Didymos with no awareness that it has become the first celestial body deliberately altered by human intention. The asteroid moon, roughly the size of the Great Pyramid of Giza, spins slowly through the cosmic dark as it has for perhaps millions of years, its surface a tapestry of regolith and boulders that record the patient accumulation of micrometeorite impacts across geological time. Its orbit, until September 26, 2022, maintained the mathematical precision of celestial mechanics, 11 hours and 55 minutes per revolution, a period as regular as atomic clockwork and as predictable as the tides. The asteroid itself possesses no magnetic field to deflect charged particles from the solar wind, no atmosphere to create weather patterns or seasonal variations, no geological activity to reshape its surface features. It exists in a state of almost perfect stasis, changed only by the gradual accumulation of cosmic dust and the occasional impact of particles smaller than grains of sand. Its gravitational field, approximately 100,000th as strong as Earth's, barely holds loose surface material in place. A gentle touch would be sufficient to launch pebbles into independent orbits around the Didymos system. Yet this same weak gravity ensures that any external force, no matter how modest by terrestrial standards, will produce measurable and permanent changes in the moon's motion. The collision that awaits Dimorphos represents the culmination of forces that began their convergence years earlier, when mission planners selected the Didymos system as an ideal target for humanity's first deflection test. The choice reflects careful consideration of orbital mechanics, observational opportunities, and safety margins. Unlike the solitary asteroids that pose the greatest threat to Earth, Dimorphos orbits within a binary system that provides natural isolation. Any change to its trajectory affects only its dance around Didymos, not its path through the inner solar system. This containment ensures that the experiment cannot inadvertently create a new hazard while demonstrating deflection techniques. The physics of the approaching impact unfold according to principles established by conservation of momentum, one of the fundamental laws that govern interactions between objects throughout the universe. When DART's 200-pound mass strikes Dimorphos at 14,000 miles per hour, the resulting momentum transfer will nudge the asteroid moon into a slightly different orbital path. The change will be small, perhaps a few millimeters per second of velocity alteration, But in the frictionless environment of space, even tiny changes accumulate over time into substantial deviations from original trajectories. A deflection that appears negligible today becomes significant across the years or decades that separate Earth from a potential impact. The asteroid's internal structure remains largely mysterious despite decades of telescopic observations and radar mapping. Ground-based studies suggest that Dimorphos, like many small asteroids, consists of a loosely consolidated collection of fragments rather than solid rock. This rubble pile architecture, held together by gravitational forces weaker than the adhesion between soap bubbles, responds unpredictably to external impacts. Some of DART's kinetic energy will be absorbed in crushing and rearranging internal components. Some will be radiated away as heat, and some will contribute directly to changing the asteroid's orbital velocity. The exact proportions remain unknown, making the mission as much a scientific experiment as an engineering demonstration. Dimorphos carries within its mineral composition the chemical signature of the early solar system. When planets were still forming from the collision and accretion of smaller bodies, its rocky components consist primarily of silicate minerals that condensed from the solar nebula at temperatures and pressures far different from those found anywhere on Earth's surface today. Metallic inclusions scattered throughout its structure preserve magnetic orientations that record the strength and direction of magnetic fields that existed when the solar system was only a few million years old. In this sense, the asteroid serves as both target and time capsule, a repository of information about cosmic conditions that prevailed before Earth had oceans or continents. The approach of DART toward its rendezvous occurs against a backdrop of celestial clockwork that has operated without interruption since the solar system achieved its current configuration. Jupiter completes its 12-year orbit around the Sun with the regularity that allowed ancient astronomers to use its position as a calendar marker. Saturn's rings continue their billion-year evolution, with individual particles following orbital paths that bring them into periodic alignment to create the gaps and divisions visible through telescopes. The Sun itself maintains the nuclear fusion reactions that have provided steady energy output for 4.5 billion years, converting hydrogen to helium at a rate of 4 million tons per second while barely affecting its total mass. Against this cosmic stability, the deliberate alteration of an asteroid's orbit represents something genuinely unprecedented in the solar system's history. Natural processes have certainly changed asteroid trajectories throughout the eons: gravitational perturbations from Jupiter, collisions with other small bodies, and radiation pressure from the Sun all contribute to the slow evolution of orbital paths. But never before has a technological civilization deliberately modified the motion of a celestial body for the purpose of demonstrating planetary defense capabilities. The event marks a subtle but significant transition in the relationship between Earth and its cosmic environment. The irony embedded in this first act of cosmic engineering lies in its target selection. Dimorphos poses absolutely no threat to Earth, making it the perfect candidate for deflection testing. Its orbit around Dimorphos ensures that the smaller moon will never approach our planet within millions of miles, while the binary nature of the system provides built-in safety margins against unintended consequences. This careful choice reflects the patience that characterizes effective planetary defense, the willingness to develop and test capabilities long before they might be needed, to learn from controlled experiments rather than wait for genuine emergencies to drive technological development. The mathematics that govern Dimorphos's response to impact derive from principles discovered centuries ago, when human understanding of celestial mechanics emerged from careful observations of planetary positions and lunar phases. These same mathematical relationships that allowed Edmund Halley to predict the return of his famous comet, that enabled space agencies to navigate robotic explorers throughout the solar system. now permit mission planners to calculate precisely how a spacecraft collision will alter an asteroid's orbital period. The equations themselves remain unchanged since Newton's era, but their application to planetary defense represents an entirely new chapter in humanity's relationship with the cosmos. The silence that surrounds Dimorphos is absolute in ways difficult to comprehend from Earth's surface, where atmospheric molecules constantly vibrate with thermal energy and where sound waves propagate through air to create the acoustic landscape of terrestrial life. In space, no medium exists to carry sound waves, making the asteroid's environment one of perfect acoustic isolation. The impact that will soon transform its orbit will occur in complete silence, witnessed only by instruments that translate electromagnetic radiation into data streams that eventually become images and measurements comprehensible to human observers millions of miles away. At precisely 23:14, Coordinated Universal Time, metal meets rock in the darkness between worlds, and physics becomes poetry. The collision unfolds in microseconds that contain the concentrated momentum of 10 months of interplanetary travel. As DART's aluminum honeycomb structure crumples against Dimorphos' ancient surface with the inevitability of gravity itself. The impact occurs at 6.14 kilometers per second, a speed that transforms the modest spacecraft into pure kinetic energy. Its carefully engineered components instantly converted to expanding plasma and debris that glows briefly brighter than the distant stars before dispersing into the cosmic void. The mathematics of momentum transfer, elegant in their simplicity, govern every aspect of the collision. DART's mass of 610 kilograms, multiplied by its velocity of 6,140 meters per second, yields a momentum of approximately 3.75 million kilogram meters per second energy equivalent to detonating 3 tons of TNT, yet applied with surgical precision to a single point on Dimorphos' surface. The asteroid, possessing perhaps 5 billion times more mass than the impacting spacecraft, absorbs this energy like a mountain accepting the strike of a pebble. Yet even this seemingly insignificant interaction produces measurable changes in its orbital dynamics. The impact excavates a crater whose dimensions reflect both the spacecraft's kinetic energy and the asteroid's internal structure. If Dimorphos were solid rock, the crater might measure 20 to 30 feet across and perhaps 10 feet deep. But the asteroid's rubble pile architecture, held together by gravitational forces weaker than the adhesive strength of tape, responds differently to high-velocity impacts. The collision's energy propagates through loosely consolidated fragments, potentially creating a crater many times larger than would form in solid material, while simultaneously ejecting debris at velocities sufficient to escape the asteroid's weak gravitational embrace entirely. The debris cloud that expands from the impact site tells its own story of deep time and cosmic archaeology. Material that last saw sunlight during the solar system's youth now streams away from Dimorphos in a luminous plume visible to telescopes across the inner solar system. This excavated regolith, composed of fragments pulverized by billions of years of micrometeorite bombardment, carries within its mineral grains the chemical signatures of processes that occurred before Earth possessed a solid surface. Each particle represents a sample of primordial material, a microscopic time capsule that preserves evidence of the conditions that prevailed when planets were still forming from colliding planetesimals. The speed at which this debris travels reveals fundamental properties of the asteroid's gravitational environment. Particles ejected at more than 40 centimeters per second, roughly walking pace, will escape Dimorphos' gravitational influence entirely, entering independent orbits around Didymos or eventually drifting away from the binary system altogether. Slower moving fragments may arc through space for minutes or hours before falling back to the asteroid's surface like cosmic snow. redistributing impact ejecta across regions far from the original crater. This process, repeated countless times over geological ages, gradually smooths asteroid surfaces and creates the fine regolith layers that characterize small rocky bodies throughout the solar system. LICHA-CUBE, the companion spacecraft deployed from DART weeks before impact, witnesses the collision from a safe distance of several hundred miles and transmits images that capture the event's immediate aftermath. The photographs reveal an expanding cloud of debris that grows rapidly from a point source flash into a diffuse structure extending thousands of miles behind the asteroid. This artificial comet tail, created by humanity's first deliberate modification of a celestial body, persists for weeks as individual particles follow ballistic trajectories determined by their exit velocities and the gravitational influences of both asteroids in the binary system. The optical properties of the debris cloud provide insights into Dimorphos' composition that would be impossible to obtain through remote sensing alone. Spectroscopic analysis of sunlight reflected by the expanding particles reveals absorption lines characteristic of specific minerals, allowing scientists to identify the types of rock and metal that comprise the asteroid's interior layers. These measurements suggest a composition similar to carbonaceous chondrite meteorites, primitive materials that formed in the outer regions of the solar nebula and preserve organic compounds and water-bearing minerals from the solar system's earliest epoch. The thermal signature of the impact registers on infrared telescopes as a brief but intense spike in radiation output from the Dimorphos system. The collision converts DART's kinetic energy primarily into heat, raising the temperature of impact debris to several thousand degrees Celsius in the first moments after contact. This thermal pulse, lasting only seconds, provides another means of analyzing the asteroid's material properties by measuring how quickly the heated fragments radiate their energy back into space. Dense metallic components cool more slowly than silicate minerals, creating characteristic cooling curves that reveal the relative abundances of different materials within the excavated debris. The momentum transfer efficiency, the ratio between the spacecraft's initial momentum and the momentum change imparted to Dimorphos, depends critically on factors that remain poorly understood until the moment of impact occurs. If the asteroid behaves like solid rock, most of the collision energy will be absorbed in creating the impact crater, with relatively little momentum transferred to the body as a whole. But if Dimorphos responds more like a loosely bound aggregate of fragments, the impact might compress and rearrange its internal structure in ways that amplify the momentum transfer beyond simple calculations based on conservation laws. The irony that emerges from humanity's first act of cosmic engineering is that success depends entirely on forces beyond human control. The internal structure of an asteroid formed billions of years before Earth existed. The gravitational dynamics of a binary system that has danced unchanged since long before life emerged in terrestrial oceans. The precise timing of orbital mechanics that brought spacecraft and target together at exactly the right moment and location in space. DART's sophisticated guidance systems and advanced propulsion technology merely serve to place the spacecraft at the correct coordinates where natural forces take over and complete the deflection according to physical laws that have governed such interactions since the universe began. The silence that surrounds the impact is broken only by electromagnetic radiation carrying information about the event back toward Earth at the speed of light. Radio signals from LICHA-CUBE, infrared emissions from heated debris, and visible light reflected by the expanding dust cloud all travel across the 14 light minutes that separate the Dimorphos system from terrestrial observers. This information, encoded in photons that began their journey at the moment of impact, will take nearly a quarter of an hour to reach ground-based receivers, where mission controllers wait to learn whether humanity's first planetary defense demonstration has succeeded in altering the course of an asteroid moon. The collision creates ripple effects that extend far beyond the immediate crater and debris cloud. The momentum change imparted to Dimorphos will gradually alter its orbital period around Didymos, shifting the timing of eclipses that occur when one asteroid passes in front of the other as viewed from Earth. This change, measurable to telescopes capable of detecting brightness variations of less than 1%, provides the definitive proof that human technology has successfully modified the trajectory of a celestial body through controlled application of kinetic energy across interplanetary distances. In the aftermath of impact, as debris continues its silent expansion into the darkness beyond Dimorphos, ground-based telescopes across Earth's night side begin their patient vigil for the first signs of orbital change. The evidence they seek manifests not as dramatic visual spectacle, but as subtle variations in brightness that occur when Dimorphos passes behind or in front of its larger companion, Didymos. These eclipses, or mutual events as astronomers term them, have occurred with clockwork precision for millions of years, their timing so regular that any alteration in the asteroid moon's orbital period becomes immediately apparent to instruments capable of measuring brightness changes smaller than 1%. The Didymos system performs its gravitational ballet at a distance of 7 million miles from Earth, close enough that ground-based telescopes can resolve the two bodies as separate objects under optimal conditions, yet far enough that the asteroids appear as mere points of light that brighten and fade according to their mutual geometry. When Dimorphos passes directly between Earth and Didymos, the smaller moon blocks a fraction of light reflected by the primary asteroid, creating a measurable dimming that lasts several minutes. Similarly, when Dimorphos moves behind Didymos as viewed from Earth, the moon's own reflected light temporarily disappears, causing another predictable change in the system's total brightness. These mutual events occur roughly twice during each 11-hour and 55-minute orbital period of Dimorphos around Didymos, a timing so precise that astronomers can predict eclipse events months or years in advance. The regularity derives from fundamental principles of celestial mechanics. Bodies orbiting under gravitational influence follow elliptical paths whose periods depend only on the orbital radius and the combined mass of the system. Any change in Dimorphos's velocity, however small, will alter its distance from Didymos and thus modify the time required to complete one full orbit. The first telescope to detect evidence of orbital change operates from the Atacama Desert in Chile, where atmospheric conditions rival those of planetary observatories and where the southern hemisphere's orientation provides optimal viewing geometry for the Didymos system during the weeks following DART's impact. The instrument, equipped with charge-coupled device cameras sensitive enough to detect individual photons arriving from deep space, monitors the asteroid system continuously during hours of darkness, building a precise record of brightness variations that serve as fingerprints for orbital dynamics. The data that emerges from these observations tells a story measured in minutes rather than millennia. Before DART's impact, Dimorphos required exactly 11 hours, 55 minutes, and 14 seconds to complete one orbit around Didymos. In the days following the collision, this period begins to shrink as the asteroid moon spirals slightly closer to its primary companion. The change amounts to only 32 minutes a shift, barely perceptible in human terms, yet representing a clear signature of successful momentum transfer from spacecraft to asteroid. The implications of this orbital modification extend far beyond the immediate demonstration of deflection capability. The 32-minute change in Dimorphos's period corresponds to a velocity alteration of approximately 2.7 millimeters per second, roughly 10 times larger than the change that would result from simple momentum conservation if the asteroid behaved like a solid object. This amplification effect, known as momentum multiplication, occurs when impact energy is transferred not only to the target body itself, but also to debris ejected from the collision site. Each particle of excavated material that escapes the asteroid's gravitational influence carries momentum away from the system, effectively amplifying the spacecraft's initial momentum through what physicists call the rocket effect. The debris cloud that continues to expand behind Dimorphos serves as visible proof of this momentum multiplication process. Spectroscopic analysis of the material streaming away from the asteroid reveals compositions consistent with carbonaceous minerals and organic compounds typical of primitive solar system bodies. These substances, formed in the cold outer regions of the solar nebula before migrating inward through gravitational interactions, preserve chemical signatures of processes that occurred when the Sun was still contracting from its parent molecular cloud and Earth existed only as a collection of smaller planetesimals. Ground-based radar facilities contribute additional measurements that complement optical observations of the brightness variations. Radio waves transmitted toward the Didymos system and reflected back to Earth carry information about the asteroid's surface roughness, rotation states, and three-dimensional shapes with resolution impossible to achieve through optical telescopes alone. These radar measurements reveal that Dimorphos maintains its spin axis orientation despite the collision, indicating that DART's impact occurred near the asteroid's equator rather than at one of its poles, where the momentum transfer might have induced tumbling or precession. The timing of successful orbital change confirmation creates its own astronomical poetry. The data arrives just as Earth's rotation carries the initial observing sites into daylight, requiring telescope operators in different time zones to continue monitoring as the planet turns. This global collaboration, coordinated through international networks of professional and amateur astronomers, demonstrates humanity's collective investment in planetary defense research, while highlighting the universal nature of the threat that asteroid impacts represent to all life on Earth. The mystery that deepens with each night of post-impact observations concerns the long-term evolution of Dimorphos's altered orbit. While the immediate change in orbital period can be measured with precision, predicting how this new trajectory will evolve over years and decades requires detailed knowledge of the binary system's mass distribution, gravitational interactions, and response to external perturbations such as solar radiation pressure. The asteroid moon's new orbit may prove stable for millions of years, or subtle resonance effects might gradually amplify the initial change until Dimorphos either collides with Didymos or escapes the binary system entirely. The radiation pressure from sunlight, negligible for objects the size of planets, becomes significant for small bodies like Dimorphos, whose mass-to-surface area ratios allow photon momentum to compete with gravitational forces over extended timescales. This Yarkovsky effect, named for the Russian engineer who first described it, can gradually spiral small asteroids inward toward the Sun or outward into the outer solar system depending on their rotation periods and thermal properties. For Dimorphos, now orbiting closer to Didymos than before, these subtle forces may either stabilize the new orbit or continue the inward spiral initiated by DART's impact. The success of the orbital period measurement validates decades of theoretical work in orbital mechanics and impact physics while simultaneously opening new questions about asteroid internal structure and binary system dynamics. The larger-than-expected momentum transfer suggests that rubble pile asteroids respond to impacts in fundamentally different ways than solid rocky bodies, with implications for both planetary defense strategies and scientific understanding of small solar system objects. Future missions may need to account for these amplification effects when calculating the energy required to deflect potentially hazardous asteroids onto safer trajectories. The irony that emerges from this first successful deflection test is that proving human capability to alter asteroid orbits simultaneously reveals how little is understood about the detailed mechanics of such alterations. DART succeeded beyond expectations, but the reasons for this success require additional investigation through both theoretical modeling and follow-up observations. The Enhanced Efficiency Asteroid Deflection Assessment (Hera) mission, planned for launch toward the Dimorphos system in coming years, will provide close-up examination of the impact crater and debris distribution to help scientists understand exactly how spacecraft momentum translates into asteroid trajectory changes. In the silence of planning rooms where humanity's future safety takes shape through equations and orbital trajectories, engineers and scientists prepare NEO Surveyor for its appointment with the darkness between worlds. This infrared telescope, designed to detect the heat signatures of asteroids invisible to ground-based optical surveys, represents the next evolution in Earth's early warning system against cosmic impacts. Unlike its ground-based predecessors that must compete with atmospheric turbulence and the limitations of visible light astronomy, NEO Surveyor will operate from the gravitational stability of the L1 Lagrange point, where Earth and Sun's combined gravitational forces create a region of space where spacecraft can maintain fixed positions relative to both bodies with minimal fuel expenditure. The telescope's infrared sensors respond to wavelengths of electromagnetic radiation emitted by objects heated by solar energy wavelengths that penetrate the cosmic dust clouds and reveal asteroids that appear as mere shadows when observed in visible light. This thermal detection capability proves particularly valuable for identifying dark asteroids composed of carbonaceous materials that reflect only 3 to 5% of incident sunlight, making them nearly invisible to conventional optical telescopes despite their potentially hazardous trajectories. These dark wanderers, remnants of the outer solar system that migrated inward through gravitational interactions with giant planets, may represent the most dangerous category of near-Earth objects precisely because of their stealth characteristics. The mission's operational strategy reflects lessons learned from decades of asteroid discovery programs that have mapped only a fraction of the objects sharing Earth's orbital neighborhood. Current surveys, limited by atmospheric interference and the requirement for nighttime observations, can detect perhaps 10% of potentially hazardous asteroids smaller than 1 kilometer in diameter. NEO Surveyor's space-based platform eliminates weather delays, atmospheric absorption, and the day-night cycle constraints that limit ground-based facilities, allowing continuous observations that will accelerate discovery rates by factors of 10 or more. The spacecraft itself resembles an enormous camera designed specifically for asteroid photography. With a primary mirror measuring 0.5 meter in diameter and detector arrays cooled to temperatures approaching absolute zero to eliminate thermal noise that would otherwise overwhelm the faint infrared signatures of distant rocky bodies. This cooling system, based on passive radiative techniques that exploit the cold vacuum of space, maintains sensor temperatures below -230 degrees Celsius without requiring consumable coolants that would limit mission duration. The engineering challenges of operating such delicate instruments in the radiation environment beyond Earth's protective magnetosphere require shielding systems and redundant electronics designed to function reliably for at least 5 years of continuous observation. The mathematical principles that govern NEO Surveyor's detection methods derive from Stefan Boltzmann's law of thermal radiation, which relates an object's temperature to the intensity of infrared energy it emits. Asteroids absorb sunlight during their day cycles and re-radiate this energy as heat during their night phases, creating characteristic thermal signatures that reveal not only their presence, but also their size, composition, and rotation periods. Dark asteroids, which absorb more solar energy than they reflect, actually appear brighter in infrared wavelengths than their light-colored counterparts. Inverting the visibility relationships that characterize optical astronomy, the telescope's survey strategy involves systematic scanning of the entire sky accessible from its L1 vantage point, building up exposure time sufficient to detect asteroids as small as 140 meters in diameter at distances extending throughout the inner solar system. This size threshold, established by congressional mandate following studies of potential impact consequences, represents objects capable of causing regional devastation comparable to the Tunguska event of 1908, when an asteroid or comet fragment exploded above Siberian forests with energy equivalent to 1,000 Hiroshima bombs. Discovering such objects decades before potential Earth impacts would provide sufficient warning time for deflection missions using technologies demonstrated by the DART experiment. The data processing requirements for NEO Surveyor's observations exceed those of most other space missions due to the computational demands of distinguishing moving asteroids from the stationary background of stars and galaxies. Each night's observations produce terabytes of imagery that must be analyzed by automated algorithms capable of identifying subtle motion patterns against backgrounds containing millions of celestial objects. These software systems, evolved from techniques developed for ground-based surveys, employ statistical methods to separate genuine asteroid detections from instrumental artifacts, cosmic ray hits, and background noise that would otherwise overwhelm human analysts attempting manual review of such vast datasets. The orbital mechanics of the L1 Lagrange point provide NEO Surveyor with observational advantages impossible to achieve from Earth's surface or even from Earth orbit. Located approximately 1.5 million kilometers sunward of Earth, this gravitationally stable region allows the telescope to maintain constant communication with ground stations while avoiding the thermal and gravitational perturbations that would affect instruments operating closer to either Earth or Sun. The positioning also eliminates Earth's shadow and atmospheric interference while providing viewing geometry that allows detection of asteroids approaching from the direction of the Sun, the same blind spot that allowed the Chelyabinsk meteor to approach undetected in 2013. The mission's integration with existing ground-based surveys creates a comprehensive detection network that combines the advantages of multiple observational techniques and viewing geometries. While NEO Surveyor excels at discovering dark asteroids and objects approaching from solar directions, ground-based telescopes continue to provide detailed follow-up observations that refine orbital parameters and physical characteristics. This collaborative approach, coordinated through international data sharing agreements, ensures that no detected asteroid escapes continued monitoring once its potentially hazardous nature has been established. The thermal modeling techniques that enable asteroid size estimation from infrared observations require sophisticated understanding of how rocky bodies absorb, store, and re-radiate solar energy across their rotation cycles. Factors such as surface roughness, albedo variations, thermal inertia, and spin axis orientation all influence the relationship between an asteroid's infrared brightness and its actual physical dimensions. These complications mean that size estimates carry uncertainties that can only be resolved through additional observations using radar techniques or close-approach optical imaging during favorable geometric conditions. The irony embedded in NEO Surveyor's mission architecture is that humanity's most advanced asteroid detection system operates by observing heat rather than reflected light, essentially watching for the thermal exhales of rocks that have absorbed millennia of solar energy during their journeys through space. These ancient wanderers, some older than Earth's oldest surface rocks, betray their presence through the infrared glow of materials heated by the same nuclear fusion processes that have powered the Sun for 4.5 billion years. The telescope thus serves as a cosmic thermometer, measuring temperatures across the asteroid populations that share Earth's orbital neighborhood. The statistical projections based on current discovery rates suggest that NEO Surveyor will catalog perhaps 200,000 new near-Earth asteroids during its operational lifetime, increasing the known population by an order of magnitude while identifying dozens of objects that follow trajectories intersecting Earth's orbital path. Each discovery adds another data point to the statistical models that predict impact frequencies and help refine estimates of the cosmic impact hazard facing Earth over timescales ranging from decades to millions of years. These models, continuously updated as new objects are found and characterized, provide the quantitative foundation for planetary defense planning and resource allocation decisions. The mission's success will be measured not by dramatic discoveries of immediate threats, but by the patient accumulation of catalog entries that collectively map Earth's cosmic neighborhood with unprecedented completeness. Most of the asteroids detected by NEO Surveyor will pose no danger to Earth for millions of years, if ever. Yet knowing their locations and trajectories provides the data necessary for long-term impact, hazard assessment, and deflection mission planning should circumstances change due to gravitational perturbations or collisions that alter orbital paths in unpredictable ways. In conference rooms where scientists translate cosmic hazards into numerical scales comprehensible to human decision-makers, the Torino scale emerges as humanity's attempt to quantify the unquantifiable, the risk that wandering stones from space might end civilization as we know it. Named for the Italian city where international experts first agreed upon its parameters. This deceptively simple ranking system assigns integer values from 0 to 10 to asteroids and comets based on their collision probabilities and potential destructive consequences. The scale operates with the clinical precision of seismology's Richter measurements, yet addresses threats that transcend any terrestrial disaster in their capacity to affect every living thing on Earth's surface. The mathematics underlying the Torino scale combine orbital mechanics with impact physics to produce risk assessments that remain valid across the years or decades that separate discovery from potential collision. An asteroid's Torino rating depends not only on its size and composition, but on the precision with which its future trajectory can be predicted, a precision that improves dramatically as additional observations refine knowledge of orbital parameters. Newly discovered objects often receive elevated Torino ratings due to uncertainties in their predicted paths, only to be downgraded as improved observations reveal orbits that safely bypass Earth by millions of miles. The scale's lower values describe objects that pose no meaningful threat to human civilization. Torino Scale 0 encompasses the vast majority of catalogued near-Earth asteroids objects whose orbits carry them safely past Earth or whose sizes make them incapable of surviving passage through the atmosphere. These cosmic pebbles and boulders, ranging from meters to hundreds of meters in diameter, would likely disintegrate as spectacular meteor showers if they did encounter Earth's protective envelope of nitrogen and oxygen. Their inclusion in asteroid catalogs reflects the thoroughness of modern surveys rather than any genuine hazard to terrestrial life. Torino Scale 1 objects represent the marginal cases where current observations suggest possible Earth encounters, but where additional data will almost certainly reveal safe passages. These ratings typically apply to recently discovered asteroids whose orbital uncertainties span ranges that include potential Earth intersections within the next century. The temporary elevation to Torino 1 serves as a flag for follow-up observations rather than a cause for concern, since improved measurements invariably narrow the uncertainty ranges until collision possibilities disappear entirely. The intermediate values on the Torino scale describe asteroids whose trajectories merit continued monitoring, but do not yet warrant active deflection preparations. Torino Scale 2 through 4 objects follow paths that bring them uncomfortably close to Earth's orbital vicinity without quite achieving the precision of prediction required for confident impact forecasting. These borderline cases highlight the fundamental challenge of long-term orbital prediction. Even tiny uncertainties in current position and velocity measurements amplify over time into substantial errors in future location calculations, making definitive statements about collision risks impossible until objects approach within a few years of potential impact. The higher Torino ratings, from 5 through 10, describe scenarios that transition from scientific curiosity to existential emergency. Torino scale. 8 objects possess both the size necessary to cause regional devastation and orbital trajectories that intersect Earth's path with mathematical certainty. Such discoveries would trigger immediate international cooperation on deflection missions. Since the lead times required for successful asteroid redirection measure in years rather than months, the scale's upper reaches. Torino 9 and 10 describe planet-sterilizing impacts comparable to the event that ended the Cretaceous period 66 million years ago, collisions capable of triggering mass extinctions through climate disruption and global environmental collapse. The irony embedded in the Torino scale's design lies in its deliberate psychological engineering to prevent public panic over cosmic threats that may not materialize. The scale's creators understood that probabilistic risk assessments, no matter how scientifically rigorous, would be misinterpreted by media outlets and government officials lacking expertise in orbital mechanics and impact physics. By limiting the scale to integer values and providing clear descriptive categories for each rating level, the system transforms abstract mathematical probabilities into communication tools that convey appropriate levels of concern without triggering counterproductive alarm reactions. The rarity of high Torino ratings reflects both the statistical nature of cosmic impacts and the effectiveness of current survey programs in providing early warning of potential threats. Since the scale's adoption in 1999, no asteroid has achieved a rating higher than Torino Scale 4, and most elevated ratings have been subsequently downgraded to 0 as improved observations revealed safe orbital paths. This pattern validates the scale's design philosophy while demonstrating that Earth's current cosmic environment contains no immediate extinction-level threats detectable with existing technology. The temporal aspects of Torino scale ratings reveal the dynamic nature of asteroid threat assessment. Objects may receive different ratings at different times as orbital predictions improve or as gravitational perturbations from planetary encounters alter their trajectories. An asteroid rated Torino Scale 1 based on limited initial observations might drop to 0 as additional measurements refine its orbit, or conversely might be upgraded to higher ratings if subsequent analysis reveals previously unrecognized collision scenarios. This fluidity requires continuous monitoring of catalogued objects and regular reassessment of threat levels as orbital knowledge improves. The scale's integration with international planetary defense protocols establishes clear thresholds for different levels of response to potentially hazardous discoveries. Torino Scale 0. Objects require only routine catalog maintenance, while Scale 1 discoveries trigger enhanced observation campaigns to resolve orbital uncertainties. Higher ratings activate progressively more intensive research programs, including radar characterization studies, spectroscopic composition analysis, and preliminary deflection mission planning. The highest ratings would presumably initiate actual deflection attempts, though no object has yet achieved ratings that would justify such extreme measures. The limitations of the Torino scale become apparent when considering impact scenarios that fall outside its design parameters. The system assumes sufficient advance warning to permit orbital determination and deflection planning, yet objects approaching from solar directions or following highly eccentric orbits might escape detection until impact becomes inevitable. Similarly, the scale addresses individual asteroid threats, but provides no framework for assessing risks from comet showers, asteroid fragmentation events, or other scenarios involving multiple simultaneous impacts. The psychological comfort provided by the Torino scale's systematic approach to cosmic threat assessment may itself represent a form of planetary defense. By transforming abstract statistical risks into concrete numerical ratings, the system enables rational policy discussions about resource allocation for asteroid detection and deflection programs. Without such quantitative frameworks, the potentially infinite scope of cosmic threats might paralyze decision-making through analysis paralysis, or conversely inspire inadequate responses based on emotional rather than scientific assessments of actual risk levels. The 0 to 10 rating system echoes other standardized scales used to communicate natural hazards, from earthquake magnitudes to hurricane categories. Yet the Torino scale addresses threats that transcend all terrestrial disasters in their potential consequences. A magnitude 10 earthquake affects regions. A Category 5 hurricane impacts coastlines. But a Torino scale 10 asteroid threatens the continuation of human civilization itself. This scaling mismatch reflects the unique characteristics of cosmic impacts as natural disasters that operate on planetary rather than regional spatial scales and geological rather than human temporal scales. The mystery that surrounds Torino scale implementation concerns not its technical accuracy, but its effectiveness in motivating appropriate responses to low-probability, high-consequence scenarios that may not manifest for decades or centuries. Human psychology evolved to respond to immediate rather than distant threats, making it difficult to sustain political and financial support for planetary defense programs that address risks measured in statistical abstractions rather than observable phenomena. The Torino scale provides a tool for quantifying these risks, but cannot solve the underlying challenge of maintaining vigilance against threats that may never materialize during current human lifetimes. In the depths of space where gravity wells intersect and orbital mechanics assume the precision of celestial clockwork, Apophis drifts toward its appointment with history. This mountain-sized asteroid, measuring roughly 100 feet in diameter and massing approximately 27 million tons, follows an elliptical path around the Sun that brings it uncomfortably close to Earth every few years. Its name, borrowed from the ancient Egyptian deity of chaos and destruction, reflects the initial alarm that accompanied its discovery in 2004 when early orbital calculations suggested a small but non-negligible probability of Earth impact during its close approach, scheduled for April 13 in 2029. The asteroid's trajectory carries it through regions of space where Earth's gravitational influence becomes significant, creating what astronomers call gravitational keyholes, narrow corridors where small perturbations can dramatically alter future orbital paths. These keyholes, typically only a few hundred meters wide in space, function like cosmic billiard table cushions that redirect approaching objects onto entirely different trajectories depending on their exact position and velocity at the moment of closest approach. For Apophis, passage through specific keyholes during its 2029 encounter could potentially set up collision scenarios for subsequent returns in 2036 or beyond. The physics governing Apophis's motion obey the same mathematical principles that Johannes Kepler derived from careful observations of Mars 4 centuries ago. Yet modern computational methods allow prediction of the asteroid's position to within a few kilometers across time spans measured in decades. These calculations account for gravitational influences from all major planets, subtle effects of solar radiation pressure, and even relativistic corrections required by Einstein's general theory of relativity. The precision achieved through such modeling approaches the limits of what orbital mechanics can provide, constrained ultimately by uncertainties in the physical parameters of the bodies involved rather than limitations in mathematical techniques. The 2029 encounter will bring Apophis closer to Earth than the orbital altitude of geostationary communication satellites, passing within approximately 19,000 miles of the planet's surface. This proximity, unprecedented in recorded history for an object of Apophis' size, will make the asteroid briefly visible to naked-eye observers as a rapidly moving star crossing the evening sky. The gravitational interaction during closest approach will alter Apophis' orbital period by several minutes, demonstrating on a cosmic scale the same momentum transfer principles that guided the DART mission's deflection of Dimorphos. Ground-based radar facilities will illuminate Apophis with radio waves during its passage, creating detailed three-dimensional maps of the asteroid's surface topography and internal structure with resolution comparable to optical telescopes, observing objects only a few miles away. These observations, impossible to achieve at any other time due to the vast distances typically separating Earth from near-Earth asteroids, will provide unprecedented insights into the physical characteristics of potentially hazardous objects. The radar data will reveal whether Apophis consists of solid rock, loosely consolidated rubble, or some hybrid structure that combines both architectural approaches. The asteroid's composition, inferred from spectroscopic analysis of reflected sunlight, suggests classification as an SQ-type object, a designation indicating surface materials similar to ordinary chondrite meteorites, but modified by space weathering processes that alter optical properties over geological timescales. This weathering, caused by bombardment with solar wind particles and micrometeorites, gradually darkens asteroid surfaces and changes their reflective characteristics in ways that complicate attempts to determine composition from remote observations alone. The close approach in 2029 will provide opportunities for detailed spectroscopic studies that may resolve current uncertainties about Apophis' material properties. The rotational characteristics of Apophis reveal a complex tumbling motion that combines spin around its principal axis with a slower wobble that modulates the asteroid's brightness as viewed from Earth. This dual rotation state, known as non-principal axis rotation, typically results from asymmetric mass distribution within the asteroid or from torques applied by gravitational encounters with planets during previous close approaches. The tumbling motion creates challenges for precision orbit determination since the changing orientation affects how solar radiation pressure influences the asteroid's trajectory over long time periods. The uncertainty regions surrounding Apophis' future positions illustrate the fundamental limits of long-term orbital prediction for objects subject to numerous small perturbations. Current observations constrain the asteroid's location during its 2029 passage to within a few kilometers. But uncertainty grows rapidly for subsequent orbits as small measurement errors amplify through repeated gravitational encounters. By 2068, when Apophis returns for another close approach to Earth, the uncertainty region spans thousands of miles, making impact predictions impossible without additional observations during intervening apparitions. The public attention focused on Apophis reflects both the asteroid's relatively large size and the dramatic nature of its predicted close approach. Yet statistically, it represents only one example of the thousands of potentially hazardous asteroids that share Earth's orbital neighborhood. Most of these objects remain undiscovered, particularly among the smaller size ranges that could cause regional rather than global catastrophes. The comprehensive survey programs now under development aim to catalog at least 90% of such objects within the next decade, providing the data necessary for long-term impact hazard assessment and deflection planning. The deflection strategies applicable to Apophis depend critically on the lead time available for mission implementation and the asteroid's internal structure as revealed by the 2029 observations. If the asteroid consists of solid rock, kinetic impact emissions similar to DART could effectively alter its trajectory given sufficient advance warning. If Apophis proves to be a rubble pile held together by weak gravitational forces, alternative approaches such as gravity tractors or nuclear deflection might prove more effective for producing reliable changes in orbital velocity without risking fragmentation. The gravitational effects that Apophis will experience during its Earth encounter extend beyond simple trajectory modifications to include potential structural changes within the asteroid itself. Tidal forces generated by Earth's gravity field, while insufficient to disrupt a coherent rocky body, might cause rearrangement of loose surface materials or trigger landslides in regions where the asteroid's internal structure cannot resist the differential gravitational stresses. These changes, if they occur, would create additional uncertainties in future orbital predictions by altering the asteroid's mass distribution and rotational characteristics. The irony of Apophis's celebrity status among potentially hazardous asteroids is that improved observations have steadily reduced rather than increased the estimated probability of future Earth impact. Initial calculations in 2004 suggested odds of approximately 1 in 37 for collision during the 2029 approach, but subsequent measurements refined the orbital parameters sufficiently to rule out impact during that encounter entirely. Current impact probabilities for subsequent returns remain extremely small, though not zero, reflecting the inherent limitations of orbital prediction across multi-decade timespans. The asteroid's mythological name proves oddly appropriate for an object that embodies both ancient fears of cosmic catastrophe and modern attempts to quantify and manage such risks through scientific observation and technological intervention. Unlike the capricious deities of ancient pantheons, Apophis follows predictable laws of physics that allow its behavior to be modeled, forecast, and potentially controlled through human agency. This transformation of cosmic chaos into manageable risk represents one of science's most significant contributions to planetary security, even as it reveals the vast scales of energy and time that characterize the universe beyond Earth's protective atmosphere. In the quiet corridors of international space agencies, where flags from dozens of nations line conference rooms and translation devices facilitate conversations across linguistic barriers, a new form of diplomacy emerges around the shared recognition that asteroids recognize no political boundaries. The Planetary-Defense Coordination Office, established within NASA's structure but operating through partnerships that span continents, coordinates humanity's collective response to cosmic threats that transcend the artificial divisions of terrestrial geography. Here, in meetings conducted in multiple languages and governed by protocols that balance scientific objectivity with political sensitivity, representatives from space agencies worldwide share data about rocks that belong to no nation yet threaten all nations equally. The mathematical universality of orbital mechanics provides common ground for these international collaborations, since Newton's laws of motion and Einstein's corrections for relativistic effects apply equally whether asteroids are discovered by American surveys, European telescopes, Japanese spacecraft, or Chinese observatories. The equations that govern celestial motion care nothing for the national origins of the instruments that detect them, creating a natural foundation for cooperation based on shared scientific principles rather than diplomatic negotiations. When an asteroid's trajectory intersects Earth's orbital path, the question of which country first spotted it becomes irrelevant compared to the collective challenge of characterizing its threat and developing response strategies. The European Space Agency's contributions to planetary defense demonstrate how international partnerships multiply observational capabilities beyond what any single nation could achieve independently. Ground-based telescopes operated by ESA member states provide southern hemisphere coverage that complements northern facilities, while space-based missions like the upcoming Hera spacecraft offer close-up investigation capabilities that extend the scientific return from impact experiments like DART. These collaborative efforts pool resources, expertise, and technological capabilities in ways that make comprehensive asteroid surveys financially feasible for participating nations. The data-sharing protocols that govern international planetary defense coordination reflect decades of experience with satellite tracking, weather monitoring, and other applications where global coverage requires multinational cooperation. Asteroid discovery reports flow through standardized communication channels maintained by the International Astronomical Union's Minor Planet Center, which serves as a clearinghouse for observations from observatories worldwide. This centralized system ensures that potentially hazardous discoveries receive immediate attention from multiple research groups capable of providing follow-up observations necessary for orbit determination and threat assessment. The technical challenges of coordinating observations across multiple time zones and seasonal variations create logistical complexities that mirror those encountered in other forms of international scientific cooperation. When telescopes in Chile discover a new near-Earth asteroid, facilities in Australia, Hawaii, and the Canary Islands must be prepared to continue tracking as Earth's rotation carries the discovery site into daylight. This global relay system requires standardized data formats, compatible instrumentation, and communication protocols that function reliably despite differences in technology, language, and operational procedures. The legal frameworks governing planetary defense activities remain largely undefined, since existing space law developed during an era when deflecting asteroids existed only in science fiction rather than engineering reality. Questions about liability for deflection missions, authority to authorize kinetic impacts on celestial bodies, and responsibility for unintended consequences of asteroid redirection attempts will require new international agreements as planetary defense capabilities mature beyond demonstration missions to operational systems. These legal considerations become particularly complex when considering scenarios where deflection efforts might redirect asteroids toward Earth, impact sites in different countries than would have occurred without intervention. The funding mechanisms that support international planetary defense coordination demonstrate both the challenges and advantages of multinational scientific enterprises. While pooled resources enable projects beyond the reach of individual space agencies, the complexity of managing budgets across different governmental and institutional structures creates administrative overhead that purely national programs can avoid. The scientific benefits of international collaboration must be weighed against these procedural complications, particularly for time-critical missions responding to newly discovered threats. The cultural and linguistic diversity within planetary defense communities enriches problem-solving approaches while creating communication challenges that require careful management. Engineering teams from different countries bring distinct perspectives on spacecraft design, mission operations, and risk assessment that can identify solutions invisible to more homogeneous groups. However, ensuring that critical information propagates accurately across language barriers requires translation protocols and verification procedures that add complexity to already challenging technical coordination efforts. The political dimensions of planetary defense coordination become particularly delicate when addressing scenarios involving nuclear deflection techniques, which remain the only available option for very large asteroids discovered with insufficient warning time for kinetic alternatives. International agreements governing nuclear weapons testing and deployment create regulatory frameworks that may complicate rapid deployment of nuclear deflection systems, even when used for planetary protection rather than military purposes. These legal constraints require advanced planning and diplomatic preparation to ensure that existential threats to human civilization do not become entangled in arms control negotiations. The asymmetric capabilities among participating nations create both opportunities and tensions within international planetary defense partnerships. Countries with advanced space launch capabilities, sophisticated ground-based telescopes, or nuclear technologies possess unique contributions to collective defense efforts, while nations with limited space infrastructure may participate primarily through funding contributions or political support. Balancing these diverse capabilities to maintain inclusive partnerships while ensuring effective threat response requires diplomatic skills that combine scientific understanding with international relations expertise. The success metrics for international planetary defense coordination extend beyond purely technical achievements to include diplomatic outcomes that strengthen cooperation for future challenges. The relationships built through collaborative asteroid research, joint mission planning, and shared observational campaigns create institutional frameworks that will prove essential if humanity ever faces confirmed asteroid impact scenarios requiring coordinated deflection efforts. These partnerships, developed during periods of relative cosmic calm, provide the foundation for rapid response capabilities that might otherwise require years to negotiate during actual emergencies. The irony that underlies international planetary defense cooperation is that humanity's first serious attempt to protect Earth from cosmic impacts emerges during a historical period characterized by terrestrial conflicts, economic competition, and political fragmentation. The cosmic perspective required for effective planetary defense, which recognizes Earth as a single vulnerable world orbiting within a universe filled with potentially hazardous objects, contrasts sharply with the nationalistic viewpoints that dominate most international relations. Perhaps the existential nature of asteroid threats provides sufficient motivation to transcend these limited perspectives. Or perhaps planetary defense cooperation represents an early indication of humanity's gradual evolution toward genuinely global consciousness. The long-term sustainability of international planetary defense partnerships will depend partly on their ability to maintain political support during periods when no immediate threats are apparent. The statistical nature of asteroid impact hazards, characterized by long intervals between significant events, creates challenges for sustaining public and governmental interest in programs that address scenarios that may not materialize for decades or centuries. International cooperation may provide political stability for such long-term commitments by distributing costs and responsibilities across multiple nations while maintaining visibility through ongoing collaborative activities. In the archives of space exploration, where mission reports gather dust and hard drives, store terabytes of images that few human eyes will ever examine, the deep impact legacy unfolds through data streams that continue revealing secrets about the solar system's most pristine time capsules. This collision between human technology and cosmic wanderer, which occurred on July 4, 2005, when a copper-clad impactor struck Comet Tempel 1 at 23,000 miles per hour, established many of the techniques and principles that would later guide planetary defense missions like DART. The encounter, designed primarily for scientific investigation rather than deflection demonstration, nonetheless provided humanity's first practical experience with high-velocity impacts on small solar system bodies. The comet that served as Deep Impact's target carries within its icy nucleus materials that formed in the outer regions of the solar nebula, where temperatures remained low enough for water, methane, and other volatile compounds to freeze into solid particles. These primordial ices, mixed with silicate dust and organic compounds, preserve chemical signatures of processes that occurred before planets existed as discrete entities. When solar heating sublimates these frozen materials during the comet's approach to perihelion, the resulting outgassing creates the characteristic tail that makes comets visible across interplanetary distances, effectively turning each comet into a natural laboratory for studying early solar system composition. The impact experiment revealed comet nuclei to be far more complex structures than the simple, dirty snowball model that dominated scientific thinking for decades. Instead of encountering a homogeneous mixture of ice and dust, Deep Impact's projectile struck layered terrain that included both consolidated regions and loose granular surfaces, suggesting internal differentiation that occurred during or after the comet's initial formation. These structural variations influence how comets respond to external forces, including gravitational perturbations that can alter orbital paths and potential deflection attempts that might be required if a comet ever threatens Earth collision. The debris cloud that expanded from the impact site contained materials spanning the full range of volatile and refractory compounds expected in outer solar system objects. Spectroscopic analysis of the excavated material revealed water ice, carbon dioxide, carbon monoxide, and various organic molecules including methanol, hydrogen cyanide, and formaldehyde substances that played crucial roles in the chemical evolution that eventually led to life on Earth. These compounds, delivered to the inner solar system through comet impacts during the late heavy bombardment period, may have provided essential building blocks for biological processes that emerged on the young Earth. The mission's success in precisely targeting a comet nucleus across millions of miles of space demonstrated navigation and guidance capabilities essential for future planetary defense applications. The Deep Impact Flyby spacecraft, approaching Tempel 1 at a relative velocity of over 60,000 miles per hour, released its impactor module 24 hours before collision with timing accuracy measured in seconds. This precision, achieved through autonomous navigation systems that track the target comet against background stars, established technical precedents for the guidance algorithms later employed by DART during its approach to Dimorphos. The energy released from Deep Impact's collision, equivalent to approximately 4.8 tons of TNT, produced a crater estimated to be 500 feet in diameter and perhaps 100 feet deep dimensions that provided calibration data for impact modeling codes used to predict the effects of much larger deflection missions. The relationship between impactor kinetic energy and crater size, modified by target material properties and impact geometry, follows scaling laws that apply across the full range of solar system collision scenarios, from micrometeorite bombardment to planet-forming impacts during the solar system's earliest epoch. The thermal and compositional mapping of Comet Tempel 1's surface, conducted during Deep Impact's approach phase, revealed regional variations in ice content and dust distribution that reflect the complex thermal history experienced by comet nuclei during their billions of years in solar orbit. Some regions appeared to be mantled with dark, refractory material that insulates subsurface ices from solar heating, while other areas showed evidence of active sublimation that creates the gas and dust emissions characteristic of comet activity. These surface heterogeneities complicate deflection planning, since the effectiveness of kinetic impacts depends critically on target material properties at the impact site. The scientific instruments aboard Deep Impact's flyby spacecraft continued observing Tempel 1 for several minutes after collision, documenting the evolution of the impact plume as it expanded beyond the comet's weak gravitational influence. The persistence of this debris cloud, visible for weeks through ground-based telescopes, demonstrated that comet nuclei contain substantial amounts of fine-grained material that can be easily excavated by high-velocity impacts. This characteristic proves advantageous for deflection applications, since momentum transfer efficiency increases when impact energy ejects material from the target rather than being absorbed entirely in crater formation. The mission's legacy extends beyond its immediate scientific discoveries to include technological and operational experiences that inform contemporary planetary defense planning. The challenges of communicating with spacecraft at interplanetary distances, coordinating observations between multiple ground-based telescopes, and processing the vast quantities of data generated by high-resolution imaging systems all provide lessons relevant to future deflection missions. These operational experiences, documented in technical reports and engineering databases, constitute an institutional knowledge base that reduces risks and development costs for subsequent planetary defense projects. The timing of Deep Impact's encounter with Tempel 1, occurring during the comet's approach to perihelion, provided observations of sublimation processes that affect comet orbital dynamics through non-gravitational forces. As solar heating vaporizes surface ices, the resulting gas jets create small but persistent thrust forces that gradually alter comet trajectories in ways that cannot be predicted from gravitational calculations alone. These non-gravitational accelerations, while typically small compared to planetary gravitational perturbations, can accumulate over multiple orbits to produce substantial changes in comet paths, including potential redirections onto Earth-crossing trajectories. The international cooperation that characterized Deep Impact's planning and execution established precedents for the multinational coordination required for planetary defense operations. European ground-based telescopes provided crucial observations during the impact event, while scientists from multiple countries contributed to data analysis and interpretation efforts. This collaborative model, refined through subsequent missions including DART and the planned Hera follow-up, demonstrates how planetary defense can serve as a unifying scientific endeavor that transcends national boundaries and political differences. The mystery that persists from Deep Impact's investigation of Temple 1 concerns the internal structure and mechanical properties of comet nuclei, which remain poorly understood despite decades of theoretical modeling and limited direct observations. The mission revealed that comets are neither the loosely consolidated snowballs once envisioned nor the solid icy rocks suggested by some impact models, but rather complex bodies with heterogeneous internal architecture that varies significantly among different comet families. Understanding these structural details becomes crucial for deflection planning, since the effectiveness of kinetic impacts depends sensitively on whether targets consist of coherent rocky materials or loosely bound aggregates of smaller fragments. The connection between Deep Impact's scientific objectives and planetary defense applications illustrates how fundamental research in planetary science provides essential knowledge for practical protection systems. The mission's primary goal involved understanding comet composition and structure to constrain models of solar system formation. Yet, the impact techniques and target characterization methods developed for this scientific purpose directly support efforts to develop reliable asteroid deflection capabilities. This dual benefit demonstrates how investments in space science create technological capabilities with applications extending far beyond their original research objectives. In the gravitational fields where celestial mechanics becomes celestial choreography, binary asteroid systems perform dances that have continued unchanged since the solar system's youth. Two rocky partners locked in orbital embraces that speak to fundamental questions about planetary formation and cosmic evolution. These paired worlds, discovered in increasing numbers as survey telescopes achieve greater sensitivity and resolution, reveal that solitary asteroids represent only one architectural solution to the challenge of persisting in space across geological time. The binary systems, comprising perhaps 15% of all near-Earth asteroids larger than 200 meters, follow gravitational rules that mirror those governing planet-moon systems while operating on scales where surface features remain visible and tidal forces create measurable effects. The formation mechanisms that create binary asteroids remain subjects of ongoing scientific investigation, with competing theories suggesting different pathways from initial rocky material to final gravitationally bound pairs. Some binary systems may form through catastrophic collisions that shatter larger parent bodies into fragments, with the two largest pieces remaining gravitationally associated, while smaller debris either escapes or eventually falls back to one of the primary components. Other binaries might originate through rotational fission, where rapid spinning causes elongated asteroids to separate into distinct components that subsequently settle into stable orbits around their mutual center of mass. The orbital dynamics of binary asteroids follow the same mathematical principles that Johannes Kepler derived from observations of planetary motion. Yet their small masses and close separations create systems where subtle effects, negligible in planet-moon dynamics, become significant factors in long-term evolution. Solar radiation pressure affects the motion of dust and small debris within binary systems, gradually removing loose material and potentially altering the mass ratios between components over millions of years. Thermal radiation from asteroid surfaces creates asymmetric forces that slowly modify orbital parameters through mechanisms collectively known as the Yarkovsky-O'Keefe-Radzievsky-Paddock effect, after the scientists who first recognized these subtle influences. The Dimorphos system that served as DART's target exemplifies the diversity found among binary asteroid pairs, with a primary body measuring roughly 2,500 feet in diameter, orbited by a moon approximately 500 feet across, at a separation distance of about 3,900 feet. This configuration, with the smaller component orbiting at a distance roughly equal to the primary's radius, represents one of the most compact binary systems known among near-Earth asteroids. The gravitational forces that maintain this tight orbital arrangement overcome tidal effects that would otherwise cause the Moon to spiral inward toward eventual collision with its parent body. The rotational characteristics of binary components often exhibit spin-orbit coupling similar to that observed in planet-moon systems, where tidal forces gradually synchronize rotation periods with orbital periods until one face of each body permanently faces its companion. This tidal locking process, operating over timescales measured in millions of years, creates binary systems where the same surface features always face toward the orbital partner. The energy dissipation that drives this synchronization process simultaneously causes orbital decay, bringing binary components gradually closer together until they either merge into contact binaries or fragment under tidal stresses. The discovery techniques that reveal binary asteroid systems to ground-based observers rely primarily on photometric monitoring that detects brightness variations caused by mutual eclipses and rotational modulations. When one asteroid passes in front of its companion as viewed from Earth, the combined brightness of the system temporarily decreases by amounts that depend on the relative sizes and surface reflectivities of the two components. These eclipse events, occurring with periodicities that reveal orbital characteristics, provide the primary means of identifying binary systems among the thousands of catalogued near-Earth asteroids. The radar observations that provide detailed structural information about binary asteroids exploit the Doppler shifts created by orbital and rotational motions within these systems. Radio waves reflected from surfaces moving toward Earth return at slightly higher frequencies than those reflected from receding surfaces, creating velocity maps that reveal the three-dimensional architecture of binary systems with resolution impossible to achieve through optical telescopes. These radar techniques, applied during close approaches when binary asteroids pass within a few million miles of Earth, produce images that show individual boulders and surface features on both components. The implications of binary asteroid systems for planetary defense planning extend beyond academic interest in solar system formation to practical concerns about deflection, mission effectiveness. Kinetic impactors designed to alter the trajectory of what appears to be a single asteroid might encounter unexpected complications if the target proves to be a binary system where momentum transfer affects internal orbital dynamics rather than heliocentric motion. Similarly, the gravitational fields of binary systems create complex environments where debris from deflection impacts might follow unpredictable trajectories rather than escaping cleanly into space. The mass ratios between binary components vary dramatically across different systems, from nearly equal pairs that orbit around midpoints between the two bodies, to extreme cases where tiny moonlets circle much larger primaries in arrangements reminiscent of planet-satellite systems. These mass distributions affect how binary systems respond to external perturbations, including gravitational encounters with planets and the gradual spiral decay caused by tidal energy dissipation. Systems with similar-sized components tend to be more stable against disruption than those with extreme mass ratios, reflecting the complex interplay between gravitational binding energy and perturbative forces. The age estimates for binary asteroid systems, derived from dynamical modeling of tidal evolution and collisional disruption timescales, suggest that most observed pairs formed within the past few million years, rather than preserving primordial configurations from the solar system's earliest epoch. This relatively recent formation implies ongoing processes that continue creating new binary systems while destroying existing ones, maintaining a population balance that depends on collision rates, rotational acceleration mechanisms, and gravitational disruption events. The short lifetimes inferred for binary systems require continuous replenishment mechanisms to maintain the observed population levels. The compositional similarities between binary components, revealed through spectroscopic analysis of reflected sunlight, support formation models that derive both asteroids from common parent bodies rather than gravitational capture of unrelated objects. The spectral characteristics that indicate surface mineral compositions remain nearly identical between paired asteroids, suggesting shared formation histories and similar space weathering experiences. These compositional constraints rule out capture scenarios that would pair asteroids with different origins and support fragmentation models where binary systems form through disruption of larger precursor bodies. The contribution of binary asteroid systems to impact hazard assessment requires consideration of scenarios where Earth encounters not isolated objects, but gravitationally bound pairs whose components might arrive at different times and locations. The orbital mechanics of such encounters depend sensitively on the approach geometry and the binary system's internal architecture, potentially creating impact patterns that differ substantially from those associated with solitary asteroids. These complications necessitate specialized modeling techniques that account for the gravitational interactions between multiple impacting bodies and Earth's own gravitational field. The mystery that surrounds binary asteroid formation reflects the broader challenge of understanding how gravitational aggregation operates in environments where collision velocities, material strengths, and gravitational binding energies interact in complex ways. Laboratory experiments cannot fully reproduce the conditions that characterize asteroid collisions, while computer simulations require assumptions about material properties and impact physics that remain poorly constrained by observational data. The binary systems themselves provide natural experiments that test these theoretical models. Yet, interpreting their configurations requires knowledge of formation processes that the systems themselves are supposed to reveal. The evolution of binary asteroid systems over cosmic timescales involves processes that operate too slowly for direct observation, yet leave signatures in current orbital and rotational states that preserve evidence of past dynamical history. Theoretical models predict that binary components gradually approach each other through tidal energy dissipation, eventually making contact to form dumbbell-shaped objects that might subsequently fragment under rotational stresses or merge into more spherical configurations. These evolutionary pathways connect binary systems to contact binaries and potentially to the formation mechanisms that created the rubble pile asteroids common among near-Earth objects. Across the world's observatories, where domed structures house instruments that never sleep and where hard drives accumulate terabytes of data with the persistence of geological processes, automated systems continue their patient cataloging of humanity's cosmic neighbors. These robotic sentinels operate with mechanical dedication that spans time zones and weather patterns, their electronic eyes sweeping across the same star fields night after night with consistency that human observers could never match. Each CCD sensor, each automated telescope mount, each computer algorithm serves as a component in humanity's first comprehensive census of the objects that share Earth's orbital neighborhood, systematic survey that transforms random astronomical discovery into methodical population statistics. The Catalina Sky Survey, Linear, NEOWISE, and their international counterparts operate according to observational strategies refined through decades of experience with the subtle art of detecting motion against stellar backgrounds. Their methods appear deceptively simple. Photograph the same patch of sky multiple times, separated by intervals sufficient for nearby asteroids to betray their presence through displacement relative to distant stars. Yet, implementing this strategy across the accessible sky requires coordination of instruments, data processing pipelines, and follow-up observation networks that collectively represent one of astronomy's most logistically complex endeavors. The software systems that process these nightly observations embody decades of accumulated knowledge about the statistical properties of cosmic debris and the instrumental artifacts that can mimic genuine asteroid detections, machine learning algorithms, trained on millions of images containing both real asteroids and false alarms, achieve detection accuracies that exceed human capabilities while processing data volumes that would overwhelm teams of human analysts. These automated systems identify potential discoveries within hours of observation, enabling rapid follow-up measurements necessary for orbit determination before newly detected objects disappear into the vastness of space. The orbital calculations that transform scattered positional measurements into precise trajectory predictions require computational resources that would have seemed fantastical to earlier generations of astronomers. Modern orbit determination software accounts for gravitational perturbations from all major planets, relativistic corrections mandated by Einstein's general theory, and subtle non-gravitational forces caused by thermal radiation from asteroid surfaces. These calculations, performed routinely for thousands of objects, demonstrate the extent to which computational astronomy has become integral to understanding solar system dynamics. The discovery statistics that emerge from systematic surveys reveal patterns that illuminate both the architecture of the solar system and the effectiveness of different detection strategies. Near-Earth asteroids appear to be discovered at rates approaching 1 per day by the most productive surveys. Yet statistical extrapolation suggests that the total population of potentially hazardous objects includes tens of thousands of undiscovered asteroids capable of causing regional devastation if they impact Earth. This gap between current knowledge and estimated completeness drives continuing improvements in survey sensitivity and coverage strategies. The international coordination required for effective follow-up observations creates a global network of professional and amateur astronomers who collectively maintain surveillance of newly discovered objects during the critical weeks following initial detection. When the Catalina Sky Survey discovers a potential near-Earth asteroid, observatories in Europe, Asia, and other hemispheres provide the additional measurements necessary to determine whether the object follows a genuinely hazardous orbit or represents a more distant main belt asteroid that poses no threat to Earth. This collaborative model distributes observational responsibilities while ensuring that no potentially dangerous discovery escapes continued monitoring. The database that accumulates from decades of systematic asteroid surveys constitutes humanity's most comprehensive inventory of any category of celestial objects, containing orbital parameters, physical characteristics, and observational histories for hundreds of thousands of small solar system bodies. These data support statistical analyses that reveal fundamental properties of asteroid populations, including size distributions, compositional variations, and dynamical families that preserve evidence of ancient collisional disruption events. The database serves simultaneously as a scientific resource for solar system research and an essential tool for planetary defense planning. The technological evolution that characterizes modern asteroid surveys reflects broader advances in digital imaging, computational processing, and automated data analysis that have revolutionized observational astronomy across all wavelengths and research areas. CCD cameras with quantum efficiencies exceeding 90% capture nearly every photon that strikes their silicon surfaces, while digital image processing techniques extract asteroid signals from noise levels that would render photographic plates useless. These technological capabilities, unavailable just decades ago, enable detection of asteroids too faint for visual observation, yet large enough to cause significant damage if they impact populated regions. The cost-effectiveness of automated survey systems, measured in terms of discoveries per dollar invested, demonstrates remarkable efficiency compared to earlier asteroid hunting methods that relied on human visual inspection of photographic plates. Modern surveys achieve discovery rates measured in thousands of objects per year while operating with staff levels that would have been considered impossibly small for comparable projects during the photographic era. This efficiency transformation enables comprehensive population surveys that provide statistical foundations for long-term impact hazard assessment and planetary defense planning. The temporal coverage achieved by coordinated survey networks approaches the ideal of continuous monitoring that leaves no accessible region of sky unobserved for more than a few nights. This systematic approach contrasts sharply with the serendipitous discovery methods that characterized earlier asteroid research, where most objects were found accidentally during studies of other astronomical phenomena. The transition from accidental to systematic discovery represents a fundamental change in humanity's relationship with its cosmic environment, transforming asteroid impacts from unpredictable natural disasters into manageable risks subject to early warning and potential mitigation. The data quality standards that govern modern asteroid surveys require positional measurements accurate to fractions of an arc-second and timing precision measured in second standards that enable orbit determination with sufficient accuracy for impact hazard assessment decades into the future. These precision requirements necessitate careful calibration of telescope optics, atmospheric correction algorithms, and reference star catalogs that collectively define the coordinate systems used for asteroid position measurements. The resulting data quality exceeds that achieved by most historical astronomical observations while being generated at rates thousands of times higher than previous surveys. The archival preservation of survey data creates permanent records of asteroid positions and brightness measurements that enable retrospective analysis of orbital evolution, rotation periods, and physical characteristics across time spans measured in decades. These historical datasets, stored in formats designed for long-term preservation, constitute irreplaceable resources for future studies of asteroid properties and solar system dynamics. The data archives also support verification of theoretical predictions about asteroid behavior and provide calibration standards for new observational techniques and instruments. The irony embedded in humanity's systematic approach to asteroid discovery lies in the contrast between the methodical nature of the surveys and the fundamentally random character of the impact hazard they address. The surveys operate according to carefully planned observational strategies that maximize discovery efficiency and minimize operational costs. Yet they search for objects whose trajectories and timing represent the outcome of chaotic dynamical processes operating across millions of years. This juxtaposition of systematic methodology with stochastic target populations reflects the broader challenge of applying rational planning to fundamentally unpredictable natural phenomena. The psychological impact of comprehensive asteroid surveys extends beyond their direct contributions to planetary defense to include subtle changes in humanity's perception of its cosmic environment. The systematic cataloging of potentially hazardous objects transforms abstract statistical risks into concrete inventories of named objects with known orbital characteristics and estimated impact probabilities. This transformation from statistical abstractions to specific threats may enhance public understanding of planetary defense issues while simultaneously creating new anxieties about cosmic hazards that previous generations never knew existed. The sustainability of long-term survey operations requires institutional commitments that span decades while maintaining political and financial support for programs that address statistical risks rather than immediate threats. The success of established surveys demonstrates that such commitments can be sustained. Yet expanding detection capabilities to achieve complete population surveys will require continued investment in technological development and operational infrastructure. The challenge lies in maintaining support for programs whose primary success metric consists of disasters that never occur due to advance warning provided by comprehensive asteroid catalogs. In the vast spaces that separate worlds, where radiation from distant stars takes millennia to traverse distances that spacecraft cross in months, asteroids continue their ancient journeys through regions of space so empty that molecules rarely encounter one another. Here, in the cosmic deep, where Earth appears as nothing more than a pale blue point lost among countless others, time moves according to orbital periods measured in years and centuries rather than the swift rotations that define terrestrial experience. The asteroids themselves. These wandering fragments of planetary formation drift through gravitational fields so weak that their own modest masses become significant factors in determining their paths through the solar system's architecture. The silence that characterizes interplanetary space represents a completeness of quiet impossible to comprehend from Earth's surface, where atmospheric molecules constantly vibrate with thermal energy and where sound waves propagate through air to create the acoustic landscape of terrestrial existence. Beyond the atmosphere's protective envelope, no medium exists to carry vibrations from one location to another, creating environments of perfect acoustic isolation where the largest explosions and most violent collisions occur without generating the pressure waves that terrestrial life associates with such energetic events. In this soundless realm, asteroids pursue their orbital dances unaccompanied by the mechanical harmonies that characterize earthly motion. The temperatures that govern asteroid surface properties fluctuate between extremes that span hundreds of degrees as these rocky bodies rotate between sunlit and shadowed orientations. During their day cycles, when solar radiation strikes surfaces unprotected by atmospheric filtering, temperatures can exceed those found in conventional ovens, causing thermal expansion that gradually fractures solid rock and creates the regolith layers observed on most small solar system bodies. The night sides of these same asteroids experience cold that rivals the deepest terrestrial winters, causing materials to contract and creating thermal stresses that contribute to the slow disintegration processes that sculpt asteroid surfaces across geological time. The gravitational environments that surround asteroids create zones of influence so weak that gentle touches could launch objects into independent orbits. Yet these same modest force fields shape the local dynamics of dust, debris, and smaller fragments in ways that mirror planetary systems operating at vastly different scales. Particles ejected from asteroid surfaces by micrometeorite impacts or thermal cycling follow ballistic trajectories that may carry them completely away from their parent bodies or return them to different surface locations after journeys lasting hours or days. This constant redistribution of material creates surface features and regolith patterns that record millions of years of such gentle bombardment. The radiation environment of interplanetary space bathes asteroids in charged particles from the solar wind, cosmic rays from interstellar sources, and electromagnetic radiation across the full spectrum from radio waves to gamma rays. These energy sources gradually alter asteroid surface properties through processes collectively known as space weathering, darkening reflective minerals and creating the reddened spectral signatures that characterize many asteroid surfaces. The same radiation that enables remote sensing observations of asteroid composition simultaneously modifies that composition in ways that complicate attempts to determine the original mineral assemblages that formed when these objects first condensed from the solar nebula. The orbital resonances that govern asteroid motion create invisible boundaries in space where gravitational interactions with Jupiter and other giant planets either stabilize or destabilize particular orbital configurations. Asteroids that drift into certain resonant relationships with Jupiter experience periodic gravitational nudges that gradually increase their orbital eccentricities until they either collide with inner planets or are ejected from the solar system entirely. These dynamical processes, operating over millions of years, continuously reshape the asteroid population and determine which objects eventually find themselves on Earth-crossing trajectories. The collision probabilities that characterize asteroid interactions reflect both the vast scales of interplanetary space and the persistence of gravitational attraction across cosmic time. Most asteroids will never experience significant collisions during the remaining lifetime of the solar system. Yet the statistical inevitability of occasional impacts ensures that catastrophic disruption events continue to fragment larger bodies and create new populations of smaller objects. These collisional cascades, occurring at intervals measured in millions of years, represent the dominant evolutionary process affecting asteroid populations throughout solar system history. The chemical compositions preserved within asteroid interiors carry information about conditions that existed during the solar system's formation, when temperatures, pressures, and chemical gradients differed dramatically from those found anywhere in the contemporary solar system. These rocky archives contain mineral assemblages that formed in environments no longer accessible to direct study, making asteroids invaluable repositories of information about planetary formation processes. The compositions remain largely unaltered by the geological activity that has modified planetary surfaces, preserving primordial materials in forms that approach their original states. The discovery that binary asteroid systems exist in significant numbers reveals that even in the apparent emptiness of interplanetary space, gravitational attraction can create complex dynamical structures that persist across geological ages. These paired objects, orbiting around their mutual centers of mass with periods ranging from hours to months, demonstrate that the weak gravitational fields of small bodies can nonetheless organize matter into architecturally sophisticated systems. The binary asteroids serve as natural laboratories for studying gravitational dynamics in regimes where tidal forces, radiation pressure, and thermal effects all contribute to orbital evolution. The future trajectories of catalogued asteroids, calculated using the most sophisticated computational methods available to orbital mechanics, extend predictions across timespans that encompass multiple geological epochs while maintaining mathematical precision sufficient for practical planetary defense applications. These calculations represent humanity's most ambitious attempts to predict the behavior of natural systems across timescales vastly longer than human civilization. Yet, they achieve accuracies that enable identification of potential Earth impact scenarios decades or centuries before they might occur. The mathematical frameworks that make such predictions possible derive from physical principles established centuries ago, yet applied with computational power that would have seemed magical to their original discoverers. The protective effect that Jupiter's gravitational influence provides for the inner solar system operates through mechanisms so subtle that their significance became apparent only through detailed computer simulations of solar system dynamics. The giant planet's massive gravitational field deflects many potentially hazardous objects away from Earth-crossing orbits, while simultaneously perturbing others into trajectories that eventually intersect terrestrial space. This dual role as both shield and source of threats reflects the complex nature of gravitational interactions in multi-body systems, where small changes in initial conditions can produce dramatically different outcomes across extended time periods. The mystery that surrounds the ultimate fate of Earth's cosmic neighborhood concerns not the predictability of individual asteroid trajectories, but the long-term evolution of the entire population under influences that include stellar encounters, galactic tidal forces, and changes in solar luminosity that will occur over billions of years. These processes, operating on timescales that dwarf those accessible to direct observation, will eventually reshape the asteroid populations in ways that current models cannot fully predict. The solar system itself exists within a galactic environment that evolves according to its own dynamics, creating boundary conditions for asteroid evolution that remain largely unknown. The stillness that characterizes the spaces between asteroids represents not the absence of activity, but rather the operation of forces and processes that unfold according to timescales incompatible with human perception. In regions where years pass between the closest approaches of neighboring objects, where gravitational perturbations accumulate over millions of orbits to produce measurable changes in trajectories, patience becomes the dominant characteristic required for understanding dynamical evolution. The asteroids themselves embody this cosmic patience, following paths determined by the initial conditions of planetary formation while remaining forever subject to the subtle influences that slowly reshape solar system architecture across geological ages. In the gentle darkness that surrounds all wandering stones, where time moves with the unhurried pace of orbital periods and gravitational conversations, the universe settles into its ancient rhythms of motion and stillness. The telescopes that scan Earth's night skies continue their patient vigil, their electronic eyes drinking starlight that carries news of distant worlds and nearby neighbors alike. The asteroids they seek drift through space with the same deliberate grace they have maintained since the solar system's youth. Each rocky fragment following paths carved by invisible forces that operate beyond human timescales, yet remain forever subject to the mathematical certainties that govern all celestial motion. The spacecraft that humanity has sent to touch these cosmic wanderers dart with its brief moment of contact, deep impact with its purposeful collision. The countless robotic explorers that have mapped and measured and photographed all become part of the larger story that unfolds in the spaces between worlds. Their metal structures, designed and built in terrestrial factories, now drift as components of the solar system itself. Their missions completed, but their materials destined to orbit the Sun for millions of years alongside the asteroids they were sent to study. The data streams that flow back to Earth from these encounters accumulate in archives where they join observations of stellar positions recorded by ancient astronomers, measurements of planetary motions that guided the first spacecraft to other worlds, and countless nights of patient watching by observers whose names have been forgotten but whose contributions persist in the growing catalogue of cosmic knowledge. Each photon captured by telescope sensors, each radio signal received from distant spacecraft, each calculation that transforms raw measurements into orbital predictions becomes part of humanity's expanding understanding of its place within the solar system's vast architecture. The silence that encompasses these activities carries its own profound meaning, not the absence of communication, but the recognition that some forms of understanding require no words. The asteroids themselves speak through their positions and motions, their surfaces scarred by billions of years of patient bombardment, their orbits encoding stories of gravitational encounters and collisional disruptions that occurred before Earth possessed continents or oceans. In learning to read these silent narratives, humanity discovers not just the mechanics of planetary defense, but deeper truths about the cosmic environment that shape the emergence of life itself. The protective systems now taking shape around Earth, the survey telescopes, the tracking networks, the deflection technologies demonstrated by successful missions represent something unprecedented in the solar system's 4.5 billion-year history, the emergence of a planetary intelligence capable of recognizing cosmic threats and developing responses to them. This capability arose not through conquest or domination, but through the patient application of curiosity and mathematical reasoning to problems that span scales from laboratory physics to galactic dynamics. As Earth continues its daily rotation and annual journey around the Sun, carrying its cargo of life through regions of space that contain both ancient debris and new discoveries, the Cosmic Watch continues. In observatories where humans and machines collaborate to catalog the contents of interplanetary space, in mission control centers where spacecraft trajectories are planned across years and decades, in the quiet calculations that transform observational data into impact probabilities and deflection requirements. The work proceeds with the same steady persistence that characterizes all fundamental processes in the universe. The asteroids themselves remain largely indifferent to these human activities, following their prescribed paths with mechanical precision while serving as unwitting participants in humanity's first serious attempt at planetary stewardship. They will continue their ancient dances long after current civilizations have passed into history, their orbits slowly evolving under influences that operate according to timescales that encompass the rise and fall of species, the erosion of mountains, the drift of continents across planetary surfaces. In this vast context of cosmic time and interplanetary space, the gentle work of planetary defense becomes not an act of defiance against the universe, but rather a form of participation in the ongoing processes that have shaped solar system evolution since its earliest epochs. The same gravitational forces that created asteroid orbits now guide spacecraft to intercept them. The same electromagnetic radiation that reveals asteroid compositions enables the communication systems that coordinate global defense networks. The same mathematical principles that govern planetary motion make possible the orbital predictions necessary for effective impact prevention. And so the universe continues its patient unfolding, with Earth a small blue world that has learned to look outward and recognize both beauty and danger in the cosmic environment that surrounds it. The asteroids that once represented only abstract points of light in telescopes now possess names, known orbits, estimated compositions, and calculated encounter probabilities. The transformation from cosmic mystery to manageable risk represents one of science's quietest yet most significant achievements: the extension of human awareness and capability into realms that operate according to scales of space and time that dwarf terrestrial experience. The stillness settles now across observatories and mission control centers, across the vast distances that separate Earth from its rocky neighbors, across the mathematical relationships that connect present observations with future possibilities. In this stillness, the work continues patient, methodical, essential as humanity learns to live consciously within the cosmic environment that gave it birth and that will, with proper attention and care, continue to shelter the long experiment of terrestrial life for ages yet to come. The sleep that comes to those who watch the skies carries with it the deep satisfaction of work that serves purposes larger than individual ambition or immediate concern. They rest knowing that the universe, for all its vastness and ancient indifference, has produced at least one world where intelligence has emerged capable of recognizing cosmic patterns and responding to cosmic challenges with wisdom, patience, and the quiet confidence that comes from understanding one's place within the grand architecture of space and time.